Bismillahirrahmanirrahim. My name is Fawaz Salam Khan. First, I would like to thanks for accepting my papers in 8th International Conference on Engineering and Emerging Technologies, Kuala Lumpur, Malaysia. I would also like to my co-authors who have helped me in this research. So today, my topic of the research, which I'm going to present here, is federated learning-based UAVs for the diagnosis of plant diseases. Before going into further deeper, I would like to first present the content of title, which includes introduction, workflow, methodology, deep learning architecture for pest classification, data set, preprocessing, augmentation, network pairing results, comparative analysis, and then conclusion. Basically, we are going to start with the introduction here. So federated learning, you need to know first federated, what is federated learning? Federated learning is an approach that address these challenges and it aim to intelligent system development through decentralized integration of various system and technologies in machine learning methodologies. Federated learning is a decentralized subset of machine learning where a technique allows the model to be trained machine learning algorithm to many local data sets without requiring the exchange of these. So this enables the creation of common global model without the need of centralized training data. So it has been beneficial for providing supportive series for the variety of applications, particularly where data confidently resource and limits and ownership become primary concern with the undertaking of data analytics. The basic concept behind the research is the technological revolution for farmers, especially for the safety of their crop from the pest, plays an evident change, you can say, for the convenience of the agriculture industry. So the current research is presented here where we are using the type of test to be predicted with the help of federated learning with the UAVs. So normally, if you are talking about in this era of revolution, UAVs are normally used for farming, for detecting different kind of pest diseases. Here we are using four different UAVs. So the state-of-art efficient net algorithm we are using with the B03 infrastructure configurations. So provides the accuracies with the help of different kind of network layers. Where we are going to have a discussion in further slides. So which will be like 99.55%. The federated learning designed UAV is the most reliable method because if the network is trained for one UAV, it will be transferred to the other system as well. So this is the workflow. If you see in the figure, there are multiple steps we are following here. A federated learning server initially generates a global model which sends to the clients in different agriculture farms. Step number two, you can say here, each client crop with the help of UAV start collect new data, disease of pest and the detection, and updates and sends the updated model parameters to the local model based on the global model. That updated parameters are periodically sent with the FL server. So step number three, you can say, when the federated learning server receives, as you see in the figure, the local model from the different clients UAVs, then the central server aggregates all the models. So step number four, the downloaded aggregated models are be sent to all the UAVs with different kind of you can say different kind of small inference models. So this is the methodology here. If you will see, the federated learning server collects the parameter of each four sites with the local models and the aggregators to create a global model. Once the federated server computes the global aggregated model, this is distributed to each client, you can say. With the help of these aggregated model, it detects the pests using the local data. As illustrated in the figure, you can see there are four distinct agriculture sites A, B, C, and D. Each site is operational with UAV that do real-time analysis to aid in detecting pests using data deep learning. Once all four sites have been trained with the local model on the local data set, the local model parameters are communicated with the federated server. So this is basically the architecture of the classification. Here we are using 344 layers with 144 with the 144 convolution layers. The kernel size is 11 cross 5 into 3. Stride we are using is 4 cross 2 into 1 with zero padding used to collect the basically max poolings. The size of the feature map here is 12 cross 12 into 8. The activation function is we are obviously reload. So the speed of the training, we use batch normalization and 100 cross 3 image sizes with the convolution layer. So by using 32 into 11 cross 11 cross 3 kernel size with 4 pixel stride pixel deficit the location between the requisite fields of the center of the adjacent neurons. So similarly, the number of parameters for different actions to be taken stored in the output layer. The final layer of our model has 6 output with the 6 output and having different results. So data sets we are using Kaggle data set. Kaggle data set is an external data set, or you can say a commercial data set. The data sets is automatically scrape and scrap images of past image from Google using Selenium and Chrome driver. And the classes are there are 9 classes. You can see include aphids, armyworms, beetles, ball worms, grasshopper, mites, mosquitoes, cephali, and stem borers. So pre-processing, we can just pre-processing the most important phase in this classification or detection. During the pre-processing stage, the patch detection technique, all the images were rescaled into 227 into 227 pixels. The system recognized the insects faster with varied image dimensions and reduce the calculation time thanks to pre-processing and insect images like that. So the patch detection techniques is run as a downsize image to use which reduce the computation time, which is very useful if you are talking about in the real time processing for the UAVs. So here we are using an augmentation technique. This reduce overfitting. We just change the size, change the dimensions of the images from 45 degrees, 60 degree, 135 and 70 degrees. So there we are producing a 600 images for each class, which is like for nine classes, it is like 5,400 images. So this is again the training technique. As I told, we are using a network training by using efficient and B3 model. Here we are using, as you earlier told, 344 layers with 7 MDC convolution models with an efficient B03. So the enhanced 150 cross 150 patch data was collected with the CNN model, and alternate dense and dropout layer exists with the dense efficient network. So finally, the classified result you have been found with the connected neurons and the conjunction with the softmax as an output layer. So this is the confusion matrix. As you see in the confusion matrix, the result seems to be like 99.55%. So the past images with an interstate context in the presence of dusk and grim pose or a difficult issue of achieving good detection output. To obtain high detection performance, we suggest a pest exposure system separates the insects from the background and picks the insects counter. The classifying accuracy and competitive analysis given the confusion matrix, as you see, a very good results which we have get from efficient net B03. So this is basically the comparative analysis between proposed model and the earlier work. The proposed model gives the accuracy of 99.55%. The earlier it was like 91.5%. Conclusion, the research revealed for 9 classes, 9 data classes, so the accuracy is 99.55%. So the algorithm identify insects with the use of detection, and obviously it goes to the UAVs which are connected towards to the federated learning server. One centralized server is designed, and you can say the algorithm is trained for one server, and it will partially, or you can say the local databases or local sets are transferred to the other UAVs. So so basically, in future, efficient B07 we can use if we want to further increase the efficiency or accuracy, you can use B07. The pest detection algorithm will be improved to identify insect with the class labels for longer insect data sets. So this is from the side. Thank you very much for my presentation.